Hello friends, in this course we have been attempting to understand the response of a material to an imposed mechanical condition. If you could recollect, we began by considering or defining what a mechanical condition is, and then we quantified how, or we saw how one can quantify the response of a material to the imposed mechanical condition. So once we have introduced what a mechanical condition is and how we can quantify the response of a material to an imposed mechanical condition, we moved into analyzing or investigating how the mechanical condition that we impose externally on the material is experienced by the material within. So this consideration of the mechanical condition experienced by the material within led to the discussion on the components of the stresses. So we began by considering or defining the mechanical condition. We also considered how to quantify the response of the material to this imposed mechanical condition, and then we saw how the external mechanical condition that we impose acts internally within the material, and this led to the discussion on the components of stress. And from there we moved to considering how to those components of stress that acts internally within the material responds. We saw there are two different responses the material offers. So first, initially in the initial stages, when you impose the mechanical condition, there is an elastic response, and beyond certain limit there is a plastic response. Now we focus largely on the plastic response. We saw, or we looked into the plastic response of the material from an atomistic point of view. We saw that there is a defect that primarily governs the plastic response of the material, or the plastic deformation of the material. This plastic deformation is nothing but the permanent change that is exhibited by the material when you impose a mechanical condition. And this particular defect that governs this permanent deformation, we refer to it as the dislocation. Now, after considering this, we are moving into a practical discussion wherein we want to see what are the different ways we can understand or study the mechanical behavior of the material physically. So far our discussion have largely been theoretical in nature, and now we want to see how practically one can understand or study the mechanical behavior of the material. So what one can do in order to understand the mechanical behavior of the material. One of the simplest tests that anyone can perform, or one of the simplest tests that was initially performed for the first time in order to study the mechanical behavior of the material, was the tensile test. If you could recollect, the term tensile, it means nothing but stretchability. So what we are essentially doing in this tensile test is we want to see the stretchability of the material. We want to impose a mechanical condition that stretches the material, and we want to see or understand the stretchability of the material. Now, even though we have been using the term material rather loosely, all our discussions have largely been confined to a specific category of the material wherein the atoms are regularly arranged in a long range manner. So this is nothing but we have been largely focusing on metals and alloys. So therefore, in the time that we have with us, we will try to include also some discussion wherein we also consider the mechanical behavior of few minutes at least to consider the mechanical behavior of polymers and ceramics. Now, getting back to tensile test. So what essentially we are doing is we are imposing a mechanical condition that allows or that enables the material to stretch, and we want to study how is the stretchability of the materials in this tensile test. Now there are different ways we have seen that one can present the results of this tensile test. So the initial way, or the way when we started conceiving about this tensile test, the first way we represented it, so say around a few years before, few decades before, even few centuries before, when the tensile test was conceived for the first time, the results or the outcomes of this tensile test was plotted in a rather simplistic way, wherein you included the load that was required to stretch the material. So the load was directly used, and the amount of the amount to which the material was stretched was represented in terms of delta L. So we have the results of the tensile test being represented in the form of load versus elongation. Now, as these studies were being performed, it was realized that this load versus elongation, even though the results that you present are accurate, even though the behavior you see is understandable, it was realized that these results were dependent on the dimension of the materials or the dimension of the sample that you consider. So in order to get rid of this influence of the dimension on the results of a particular test, we normalize each of these parameters with the initial dimension. We normalize the load with respect to the initial cross-section area, that is A0, which rendered as the stress, and we normalize the deformation or the elongation with respect to the initial dimension that rendered as the strain. So ultimately, the next stage of representing or presenting the tensile test or representing this tensile test was in the form of stress versus strain curve. Now, even though this particular representation was got rid of the influence of the dimension of the specimen on the results that you get, there was a certain degree of ambiguity associated with it. So this ambiguity, we saw that beyond certain point, the stress that is supposed to increase with strain began to decrease. So initially this was the ambiguity that was introduced by this particular representation of the tensile test. However, we were able to understand where this ambiguity comes from. But even though we were able to understand that, even though there wasn't, since the ambiguity is present in the first place, people wanted to get rid of it, and they wanted to arrive at a true expression for the tensile test, or true way of representing the outcome of the tensile test, and that is where we end up having the true stress strain curve, true stress and true strain curve. So these are the different ways one can represent the outcome of the tensile test. So however, now it is important for us to realize in the context of the practical testing or practical tensile testing, in this context it is important for us to understand, even though the most accurate way of representing the tensile test is by means of using true stress and true strain, it is quite difficult for few reasons. One of the reasons is the definition of the true stress. It demands the calculation of the instantaneous area. So the problem with the stress strain curve, the engineering stress strain curve, was you get a representative curve, particularly for metals and alloy, which looks something like this. Now this was the problem, or this was the point that rendered the ambiguity to the representation in engineering stress and engineering stress strain curve. So this was the problem, or this was the point that introduced ambiguity, because before this point we had an understanding that with increase in the stress or with increase in the strain you need to increase the stress. However, beyond this point there appears to be a change, a drastic change, and we saw that this change was primarily due to the necking or geometrical change in the sample, and we were able to account for this change in the behavior or this rather ambiguous point. Now, once we have gained such an understanding of the overall behavior of the engineering stress strain curve, then it is easy for us to interpret the engineering stress strain curve to that of the physical behavior that you see. Now, initially when we didn't know what this point meant or what is the reason behind this point, we wanted to look for a different way of representing it. And that is the reason we came up with true stress strain curve. But now that we have understood what is the reason for this particular point, beyond which the stress decreases with increase in strain, it is now convincing for us to use the engineering stress strain curve. And the other reason is because, like we saw here, for calculating or for plotting the true stress strain curve, you need to calculate the instantaneous area at every given moment, and that requires a sophisticated set of machines. So therefore, the cost of tensile testing proportionately increases when you want to represent your results directly in true stress strain curves. So when you want to do the stress test rather, and then you want to represent or present the results directly in the form of true stress and true strain, then you need to have a sophisticated setup, and the cost of the test proportionately increases. So that is another reason why people have considered the engineering stress and engineering strain. Even though there is some sort of an ambiguity associated with it, people have stuck with engineering stress and engineering strain representation of the results that come from the tensile tests. The other reason is we have also seen that it is possible for us to translate the results that we get in terms of the engineering stress and engineering strain to that of true stress and true strains. So even though your machineries or the setup that you get will render you the results that are based on the engineering stress and engineering strain, through some numerical operation, it is possible for us to convert the engineering stress and engineering strain to that of the true stress and true strain. So for all these reasons, the conventional or the most accepted representation of the tensile test results have been engineering stress and engineering strain. So when you talk about from the tensile test from the practical point of view, even though there are different ways of representing the outcomes of the tensile test, the most preliminary way of using load and deformation, the other way of using engineering stress and engineering strain, and the final way or the most accurate way of true stress and true strain, even though all these different setup or all these different ways are available for us in order to represent the results of the tensile test, we generally use engineering stress and engineering strain because, one, when compared to the load and deformation, it is independent of the initial dimension. Secondly, even though there is some ambiguity associated with this, now we are in a position to understand where this ambiguity comes from. And thirdly, to calculate the true stress and true strain directly, we need to have a sophisticated machine, so that increases the cost of testing. And finally, even though we arrive at the engineering stress strain curve from the testing machine, it is possible for us to convert that to true stress and true strain. So given all these reasons, conventionally when you talk about the tensile testing, the result that you get is usually in the form of engineering stress and engineering strain curve. Now we have seen there are different properties that one can calculate from the stress strain curve. So let us again stick with the engineering stress strain curve. So let us consider a representative one. So it comprises of a linear region and a non-linear region. So the linear region, so this region here is where the material experiences the elastic deformation, and the slope of this region we refer to as that as the modulus of elasticity. So we have a section in the engineering stress strain curve wherein the stress and strain are linearly related and the constant of proportionality is the Young's modulus. And there is a point beyond which this linearity is lost, that we refer to as the proportionality limit. So in the elastic region, there is a linear relation between the stress and strain, and beyond certain point this proportionality or this linear relation between stress and strain is lost, and that we refer to as the proportionality limit. And this can also be referred to as the elastic limit, because beyond this point the elastic deformation is accompanied by plastic deformation. You have combination of elastic and plastic deformation beyond this point. So you have Young's modulus, you have proportionality limit, or we can also refer to that as the elastic limit. So beyond this point, so elastic limit and the proportionality limit are the maximum stress beyond which, or the maximum stress till which you can have exclusively elastic deformation. So you have a maximum stress till below which you can have exclusively elastic deformation, and above which there is a certain degree of plastic deformation that sets in. Now that we have understood what a plastic deformation is, so we saw the plastic deformation is nothing but it is governed by rather purely, in the previous lecture we saw that the plastic deformation is governed by the increase in the number of dislocation and also the average movement or the average distance covered by the dislocation. So therefore, in addition to the elastic limit being purely a theoretical concept, so the elastic limit is also the stress at which there is not much, the maximum stress at which there is not much discernible mobility of the dislocations. Now we saw, even without the imposition of the stress, even without the mechanical condition being imposed, there is a formation of dislocation, and only when you impose the mechanical condition, only when you have plastic deformation, this dislocation begins to move, thereby rendering the, or thereby introducing the plastic deformations. So you have in the polycrystalline material already some amount of dislocations that are present, and when you impose the stress, these dislocations begins to move and they ultimately contribute to the plastic deformation. Now the elastic limit, or you can say the true elastic limit, is the maximum stress below which there is not much discernible movement of the dislocation. Now if you observe a discernible movement of the dislocation, what I mean by discernible movement is when you are doing what you commonly call as an in situ testing of the material. You tensile test your material within the microscope and you observe what are the behavioral changes or microscopic changes that the material exhibits. When you do the tensile testing within the microscope, if you are able to discern that there is a dislocation movement, then you are beyond the true elastic limit. So this idea of true elastic limits comes from our understanding of dislocation. So even though we are already familiar with Young's modulus, proportionality limit, the elastic limits, particularly true elastic limit, when you do a tensile testing within a microscope, the discernible movement of the dislocation means we are beyond the true elastic limit. Now all these concepts, particularly the proportionality limit and the elastic limit, when we talk in the context of this engineering stress strain curve, they depend on the sensitivity of the material that you use. So more sensitive your material is to that of the deformation, the more precisely you will be able to calculate the proportionality limit or the elastic limit. So since it depends on the nature of the material of the testing mission, people have found, or an alternate approach is generally proposed in order to find the stress beyond which you have plastic deformation, and that we refer to as the yield stress. So yield stress is or yield strength is the stress beyond which we have plastic deformation or observable plastic deformation. So in order to calculate this yield strength, we consider an offset strain which is usually 0.02%, and based on this offset strain, we plot a straight line, and the point where this line that is constructed based on the offset strain intersects with the stress strain curve, we call that point as the yield strength. Now since we use this offset approach, this is referred to as the offset yield strength. Now this offset value can be different. Some can choose 0.01 value, some can choose 0.001 value. It again depends on the sensitivity of your machine. So, but the approach remains the same. That is, you choose an offset value, an offset amount of strain, and from that strain you construct a straight line, the slope of which is equal to the slope that you observe in the elastic region. So the slope of this line here and the slope of the offset line here, they are equal, and the point where this offset line meets with the stress strain curve, we refer to it as the yield strength. And since we had to take an approach of that is based on the offset, we refer to it as the offset yield strength. And depending on the place this particular test is being done, supposing if this test is being done in the British Isles, they refer to this as the proof strength. So the offset yield strength and the proof strength are more or less the same. They have the same. These are determined by the same approach. But however, depending on where it is being done, particularly if you do it in say British nations, they refer to it as the proof strength. Now, in addition to these different values, we also have one particular point here, which is referred to as the ultimate tensile strength or the tensile strength alone. So this is the point wherein the system is able to accommodate the sufficient amount of stress before it exhibits any change geometrically. So maximum stress a system can accommodate before it can exhibit or before it can change geometrically is referred to as the universal or ultimate tensile strength rather. So these are the different factors or different properties that one can calculate from the stress strain curve. So all these we have seen in the previous lectures as well, and this is just the recap of what we have seen in the context of the testing of the materials. Now again, all these tests or the perspective that we are offering to the consideration of the stress strain and these different properties is from a practical standpoint. We want to see the behavior of the material by testing them. We don't want to talk about them theoretically. We don't want to talk about them in terms of the internal changes that we see within them. We want to talk the behavior of the material from the physical standpoint, from the observation that we observe when we do the test on the material. So we do a tensile test on the material, and we want to talk about its behavior from the physical changes that we see. Now, in that case, when we are purely giving a practical approach to the tensile testing, one other term that helps us understand the behavior of the material to the imposed mechanical condition is the term ductility. So given that our perspective now has changed from a purely theoretical one to that of a physical one or an application oriented one, we want to talk about the behavior of the material in terms of its applicability, in terms of its usage. And we are talking not in the theoretical sense or a precise sense. We are just talking about the behavior of the material. We want to talk about how a material responds to a mechanical condition from the physical standpoint, from the application standpoint. Then this term ductility helps us hugely. So this ductility term, it doesn't have a precise definition, but it is a qualitative description. You need to understand that this term, it doesn't have a precise definition. Like you cannot say, okay, this is the ductility, this is the value of the ductility, but it is a qualitative description that enables us to compare different mechanical behavior of the material. So you can, instead of when you want to consider a single material and want to talk about its properties, then you go for quantitative parameters like Young's modulus, proportionality limit, yield strength, and all these parameters that we have considered so far. When we want to talk about a single material and talk about its mechanical behavior, we have to be quantitative, and we talk in these terms. However, if you have few materials with you and you want to say that this material behaves in this particular manner when compared to all the other materials, you want to talk about, or when you want to distinguish one material from the other, and you want to say, okay, this material behaves in a different manner when compared to all these materials. In that case, the term ductility comes into play. So from a practical usage point and from the physical standpoint, the term ductility plays a role. So what this ductility is, it is nothing but the ability of the material to undergo changes before it fails. So the ductility is a qualitative description, it is not a quantitative one. So the qualitative description of the ductility is nothing but the ability of a material to undergo deformation before it fails. So the amount of deformation that a material can withstand before it fails is what we refer to as the ductility. There is another wonderful way of thinking about it. The more the material is forgiving, you impose a stress on the material, you keep on stressing the material, and if it is keep on forgiving, the more forgiving the material is to the stress you impose, the more ductile your material is. So the physical description or the qualitative description is the more deformation that a material can experience before it fails is referred to as the ductility. So since we have this qualitative or rather a generalized definition, we can use certain expression to calculate the ductility rendered by the material. So ductility is the amount of deformation a material can experience before it fails. So then the strain exhibited by, or to quantify the ductility of the material, we need to consider the strain exhibited by the material before it fails, or the deformation that is exhibited by the material before it fails. So that means what we essentially have is, once you consider a sample like this and you keep on imposing the stress, a tensile stress to the sample, so there is a change in the dimension of the sample, and after a change in the dimension of the sample begins to neck, and after the necking event, the sample begins to fail. Now, since the ductility is defined as the ability of the material to withstand passive deformation before it fails, then it can be quantified by calculating the dimension of the material before it fails, or even after it fails we can put it together and calculate a dimension. So let this be LF, and let this be L0. So the ductility is nothing but LF minus L0 by L0. So it is the strain after the material has failed. So this gives an expression, or this helps us to quantify, even though ductility is a qualitative term, this helps us to quantify the ductility of the material. So by calculating the dimension of the material at the moment of its failure or once it has failed, and then by relating it to the initial dimension, one can calculate the ductility of the material. The same can be done for the change in the area. So A0 is the initial cross-section area and AF is the final cross-section area, and by doing so you can also calculate the, or to a certain degree measure the ductility of the material. So ductility is nothing but, the general definition is nothing but the ability of the material to withstand any deformation before it gives in and fails. So when you compare a different set of materials, and when you say that this material is more ductile than the other, it means this material can withstand a sufficient amount of stress and deform without failing when compared to the rest of the material. So that is exactly what we mean by ductile material. It's a qualitative term, it's also a subjective term, and it helps us to relate one material to another material based on their mechanical behavior. Now, in addition to ductility, there are other terms that are used from the application standpoint and from the physical, or when you are doing the testing of the tensile testing of the material. So one term is the ductility, the other term is resilience. So this resilience, this is again, even though ductility is a term that is associated largely with technical discussions, resilience is a term that you might have come across in some other context as well. So the resilience is nothing but the ability to experience this change and get back to your original form. So the resilience in the general context is just to face different situation and not to lose your form. So similarly, in this context as well, the resilience is the ability of the material to absorb energy and get back to its original form. So if you have a material, you impose the mechanical condition, thereby you are imposing some sort of an energy into the system. And once you release the mechanical condition, the ability of the system, even after accommodating the amount of energy that you impose, the ability of the system to get back to its original form by releasing this energy is what we refer to as the resilience. So it is nothing but, when we talk about a material deforming and getting back to its original form, we are then confined to the elastic region. So in the stress strain curve, you have your elastic region that is characterized by the linear relation between the stress and the strain. So in this region, the resilience is nothing but the ability of the material to absorb energy during loading condition, and when you release it, to release the energy and get back to its original form is what we refer to as the resilience. So if you could impose a mechanical condition such that the strain is at this point, you have imposed this much amount of stress, and now the material is strained to this point. And now when you impose the stress, the material has gained some energy, and because of the energy, it has translated this energy to the strain that we see. And once you release the mechanical condition, it will release this energy and get back to its original form. And this is the amount of energy that is observed and released when you impose or load the material and you unload it is what we refer to as the resilience. So the resilience is within the elastic limit, because once you unload it, the material would regain its original form. And secondly, it is the energy that the material observes during this deformation and getting back to its original form. This is what we refer to as the resilience. So resilience is the energy observed by the material when you load it, and it exhibits a change in the dimension, and once you unload it, this energy is released and it gets back to its original form, and this energy is what we refer to as the resilience. So resilience is the energy, and that is operating within the elastic limit, and it is observed when you load it, and it is released when you unload the sample. Now if you could recollect, the energy we saw in our previous discussion, when we considered the energy that is introduced by the dislocation, we refer to that as the strain energy, and here again the resilience is nothing but the strain energy as the product of the stress and strain. So in this case, if I'm talking about this point here, I'm imposing a certain amount of, or I'm introducing a certain amount of strain energy by loading the material to sigma 1, and the strain that is exhibited by the material is epsilon 1. Now once I unload it, there is a certain amount of energy that is being released and the material gets back to its original point, that is here to the origin. Then the energy that is released and absorbed when you unload and load respectively is the product of, is expressed in this manner, that is sigma 1 and epsilon 1, and this is nothing but the area under this curve here. So therefore the resilience is nothing but the area under the section or the elastic section of the curve, which considers or which quantifies the energy absorbed by the material when you load it and the energy released by the material when you unload it. So this is what the resilience quantifies. So the resilience quantifies the energy, and when you plot this energy in the stress strain curve, it is nothing but the area under the elastic region of the curve. So resilience is the energy absorbed and released when you load and unload a system within its elastic limit in the context of the stress strain curve, because the energy that is absorbed and released, particularly the strain energy, this is nothing but the strain energy, that is what is absorbed and released, is of this form, that is half the product of stress and strain. Given that it is nothing but the area of the particular triangle that we have here, it is nothing but the area under the elastic region of the stress strain curve. So an area under the elastic region of the stress strain curve, it quantifies the resilience, which is nothing but the strain energy that is absorbed and released when you load and unload a system within the elastic limit. Now there is another term that is used to characterize the mechanical behavior of the material from a practical standpoint, and that is toughness. Now toughness is also the amount of energy that is being absorbed by the system. However, in case of toughness, it is the amount of energy that is absorbed before the material fails. So similar to ductility, which is nothing but the amount of deformation the material can exhibit before it fails, in toughness is the amount of energy, again this is an energy related term, so amount of energy a material can absorb before it fails. So that means when you consider the overall stress strain curve that includes both the elastic region and the plastic region, the toughness is the area under the overall curve. So this is what we refer to as the toughness. Now we have resilience that is associated with the elastic limit, and is the energy absorbed and released when you load and unload within the elastic limit, and we have toughness, which is nothing but similar to the resilience. It is the energy absorbed by the material, but it is not just confined to the elastic limit, but it is confined through the overall life of the material during testing. So the energy absorbed by the material before it fails or till it fails is what we refer to as the toughness. So the overall area under the stress strain curve is this toughness, and the area under the stress strain curve before the elastic limit, we refer to that as the resilience. Now when we are talking about the tensile testing of the material, there is one aspect that we need to consider. So this aspect we saw it even in moments before, or in the initial stages of this lecture as well. So this is referred to as the instability of tension. So instability of tension or tensile testing. So this is something that we need to keep in mind when we are studying the mechanical behavior of the material using tensile tests. So what do you mean by instability of the tension? So this is nothing but a specific point in the stress strain curve that is characteristically associated with the tensile tests. So there is, when you present the outcomes of the tensile test, in this outcome there is a characteristic point that is exclusively due to the nature of the test. So you can do different tests or you can study the mechanical behavior using different tests. However, there is one characteristic behavior, or there is one characteristic point that is exclusively offered by the tensile testing, and this point is what we refer to as the instability of the tensile test. And this point is none other than the point that we have already seen, which is the ultimate tensile stress. So this peak here is what we refer to as the instability of the tensile stress, because generally we construct a system or construct a stress test in such a way that we get an idealized result. However, in case of the tensile testing, we have the change in the geometry of the specimen introducing or influencing significantly, not just mildly or marginally, significantly the outcomes of the tensile test, and that is what we refer to as the instability of the tensile test or instability of tension. So there, when you do the tensile test, in addition to all the phenomenological or all the changes that are expected in the material, there is an additional change that influences the overall result that you get, that significantly influences the overall result that you get, and that we refer to as the instability. So what causes this instability is that in this region we have strain hardening. So we saw in the context of the dislocation, when you increase the increase the stress that you impose on the material, there is an increase in the dislocations. So the dislocations multiply, and once you have the dislocations multiply, their movement is rather restricted, and therefore you need to increase the amount of stress in order to increase the plastic strain. So when you introduce plastic deformation, and when you keep on introducing plastic deformation, the number of dislocation increases, and this number of increased dislocation restricts the movement of the dislocation. So in order to add to the existing strain, you have to increase the plastic deformation. So that is the reason why you have continual increase in stress. So beyond this point, beyond the elastic limit, you have a continual increase in stress as you increase the strain. However, beyond this point, there is a decrease, and this is because you have the necking, you have a geometrical change in the material. So the cross section of the material decreases. Now, even though in the initial stages, when there is a marginal change in the cross section, even because of the strain hardening, there is a balance between the necking and strain hardening. Let me repeat, necking, what it does is increases the stress that is required for plastic deformation. So strain hardening, it increases the stress that is required for plastic deformation. However, necking, what it does is, by decreasing the cross-sectional area, it decreases the stress that is required for plastic deformation. So this doesn't mean that once the necking starts, the decrease in the curve begins. It does not mean that, because in the initial stages, there is a balance between the necking and the strain hardening. Even though the necking causes a marginal decrease in the cross-section area, because of strain hardening, there is a balance. And this balance between the necking and strain hardening is what leads to this point here. This peak doesn't mean that necking has begun in that region. This peak means there is a balance between strain hardening, which increases the stress required for plastic deformation, and necking, which decreases the stress required for plastic deformation because you have reduced the cross-sectional area. So there is a balance between the strain hardening and necking, and that is what is characterized by this point here, and that is what the instability means. Once this balance is lost, then the influence of necking, the influence of the geometrical change becomes more pronounced. So the instability begins when the balance between the strain hardening and necking is lost. So therefore, when you consider this in the generalized term of the load versus elongation, this is a peak, therefore at that peak the derivative is 0. So you have a peak by considering the geometrical nature of the curve, and we assume that we have constructed this curve by considering load and elongation. So in this peak, the first derivative is 0. Now it is important for us to understand, in addition to the stress that is varied, because we are changing the stress in order to increase the plastic deformation, in this instability, the necking since it is already introduced, there is also a change in the cross-sectional area. So therefore, the first derivative needs to be expressed using the chain rule as this. Since both stress and the cross-sectional area changes at the point of the instability, wherein you have the balance between strain hardening and necking, using the chain rule, since you have multiple variable, using the chain rule, the first derivative or the condition for the peak should be expressed in this manner. Now we can rearrange these terms and express this as minus of this, and then rather it's minus of dA by A. So this is the condition that characterizes the instability in tension. So we have a purely mathematical condition that talks about the instability in the tension, and since we have several variables, more than one independent variable that is operating at that point, we to introduce chain rule, and based on the chain rule we are rearranging it, and we are ultimately ending up with this expression here. Now given that this is nothing but the change in the area with respect to the original area, that is nothing but the description of the strain that we have with us. So what we are essentially talking about is relating the change in the stress to that of the strain. You can replace this term here, since this is nothing but the strain that is exhibited at that point, that is dA by A, and since it is necking, there is a reduction in the cross-sectional area, it is nothing but the strain that is experienced by the material. You can substitute this here, and ultimately the condition that characterizes the instability is this. So the change in the stress with respect to strain, when it is equal to that of the stress, it is what characterizes the instability in tension. Now using this relation here, you can identify the point where the necking begins even in the true stress strain curve. So you have the engineering stress strain curve that clearly states where the necking begins more pronounced, where the necking becomes dominant. However, that is not easy for us to identify that in the true stress strain curve, and using this instability condition, it is possible for us to geometrically construct a tangent and then identify when the tangent is equal to that of the stress, then that point is where you have the instability or the dominance of necking begins to be more pronounced. So this is largely associated with the tensile testing. So whenever we want to talk about, or when we are talking about the tensile testing, we cannot do that without considering the instability that is associated with it, and that instability is quantified by considering this expression here. So this instability can be identified. So in engineering stress strain curve, it is easy for us to identify it because there is a significant change in the relation between the stress and strain. However, in case of true stress strain curve, it is difficult for us to identify, and this relation helps us to identify the instability condition and tension. Now finally, in order to wind this lecture up on the tensile testing, let us consider the influence of strain rate. So what we essentially do is, when we consider or when we study or test the tensile properties of the material, we, instead of increasing or imposing the mechanical strength, practical way of doing the tensile testing is by imposing a definite amount of strain at regular periods and studying how much of a stress is required to impose this strain. So I posed a similar question when we initially introduced the stress strain curve, and this is the answer to it. When we are working or when we are practically testing the tensile properties of the material, it is easy for us to govern the strain that we introduce on the material than the stress that we introduce on the material, because when we consider or when we control the test by controlling the stress, we need to look for the necking, and then once the necking begins, we have to automatically reduce the stress that is required to cause the elongation. However, when we do the test the other way around, we fix or we govern the test based on the amount of strain that you introduce, then even after the necking sets in, to introduce a given amount of strain, the stress that is required automatically decreases. So therefore, instead of considering or governing the whole tensile test based on the stress, the whole tensile test is planned based on the rate of strain or the strain that we impose on the system. So when you consider or when you construct a tensile test that is based on strain. No matter whatever geometrical change the material experiences or the specimen experiences, you get the representative stress strain curve. However, when your test is based on the stress, then you have to be careful about the cross-sectional area, and once you observe the decrease in the cross-sectional area, then you have to be very careful about the amount of load that you impose so that it is proportional to that of the cross-sectional area. So in order to avoid that, generally people devise the tensile test based on with strain as its controlling parameter. So they give different amount of strains, they keep on increasing the strains, and they calculate how much of the stress is required, and they plot the stress strain curve. Now in that case, the rate in which the strain introduced plays a role in the stress strain curve. So this role of the strain rate, the rate at which the strain is introduced during tensile testing, the role it plays is identified by its influence on the flow stress. So if the flow stress is nothing but the amount of stress that is required to add to the existing plastic deformation. So we saw that during strain hardening, to add to the existing plastic deformation, you need to increase the amount of stress that is required. And this stress that is required to add to the existing plastic deformation or introduce the plastic deformation is what we refer to as the flow stress. So the flow stress that is required to increase the plastic deformation in a material, this increases with increase in strain rate. So when you increase the strain rate, say you want to increase the amount of plastic strain from 1 to 2, when you increase the strain rate, the amount of stress that is required to add to the plastic deformation or move from point 1 to 2 also increases. The reason is because when we talk about strain or rate rather, we are introducing the concept of time. And when you are talking about increased strain rate, then you are reducing the time between two strains. And the plastic deformation, if you could recollect, it depends on the average moment of the dislocation. And when you are reducing the average moment of the dislocation, then to increase the amount of stress, you need to to add to the existing plastic deformation, which is now governed by the reduced plastic or reduced moment of the dislocation. You need to increase the amount of stress that is required. So therefore, by increasing the strain rate, you are allowing or restricting the movement of the dislocations, and therefore you need to have an increased flow stress to increase or to add to the existing plastic deformation. So other factor that governs the stress strain curve is the temperature. So in order to understand the influence of temperature, people do high temperature tensile testing. So the way the temperature influences the tensile test is it increases the ductility of the material, and it reduces its strength. Now the reason the material becomes more plastic at high temperature is because when you increase the temperature, you introduce or add to the energy of the system, you introduce thermal energy to the system. So this thermal energy increases the mobility of the dislocation, and therefore the dislocations easily move. That means the plastic deformation is enhanced, and that means the ductility also is enhanced. And similarly, when you have a temperature that increases the energy of the dislocation, or that adds to the energy of the dislocations through the thermal energy, new slip systems get activated. The dislocation are allowed to move in different slip systems, and that also enhances the plasticity. Therefore, the plasticity is enhanced with the increase in temperature, and the plasticity then sets in much below the yield strength at the room temperature, and therefore the yield strength is reduced, and the ductility of the material is increased with temperature. So temperature increases ductility and it reduces yield strength. However, the strain rate, an increase in strain rate, it increases the flow stress that is required to add to the plastic deformation. So with this, we will wind up our discussion on the tensile testing, and we will consider other testing approaches in the upcoming lectures. Goodbye.